Okay, let's finish talking about changes or physical changes before we get to chemical changes. And the last thing we need to look at is called a heating curve. And yes, I know it's not exactly curvy, but that's what it's called. And so a heating curve kind of puts together all the things we've been talking about, changing state and changing temperature. And if you take a look at what's going on with our heating curve here, we have temperature over here on the y-axis, and we have heat added and this is in kilocalories, it could be kilojoules, it could be whatever. You could also look at this as time as heat is added. But the important part is what's going on along each of our little sections of our graph, okay? So if you'll notice on this first little sloped section, it says ice. So this specific heating curve is for water. And anywhere where we start the curve, the temperature is less than 0, which means we're in the solid phase, we're in ice. And going all the way up this curve to this corner right here, what's happening to the ice? Well, it's changing temperature. So right here, this is going to be a temperature change. So if we wanted to calculate how much heat is involved there, we would have to use our Cm delta T formula, okay? Now, at that point right there, the graph stops changing temperature. And you can see we're adding heat, adding heat, adding heat, but the temperature is staying constant. So at this part of the graph, okay, we're changing from ice to water, and that is melting, which is the heat of fusion, okay? So we would have to do a calculation here with the heat of fusion. And then once all of that ice has turned into water, then the water can start changing temperature again. So in that part of the graph, we're going to go back to the Cm delta T formula to calculate how much heat is involved. Then we get to another corner, and you'll notice this one happens at 100 degrees Celsius. So as we add heat to water at 100 degrees Celsius, what's it going to do? It's going to vaporize. It's going to turn into water vapor. So all along this part of the graph, right here, this is going to be the heat of vaporization. So we would use that conversion factor in our calculation. And then once we get to this point and we've turned all of that water into water vapor, then the temperature can start going up again. So we would go back to using our Cm delta T. So technically, we could have 5 separate calculations. If we wanted to know how much heat does it take to change ice from way down here all the way to steam way up here, we would have to do 5 separate calculations to figure that out. And that's what we're going to practice next. All right, so our question says, how much heat is needed to convert 3.5 grams of ice at negative 15 degrees Celsius to water at 35 degrees Celsius? So if we go back to our heating curve, we're basically starting here. So we're going to heat up the ice, then we're going to melt the ice, and then we're going to raise the temperature of the water to about here. So we're going to have 1, 2, 3 different calculations that we have to do. So we'll call those sections A, B, C. All right, so let's start with section A. All right, what's happening in section A? Well, the ice is starting at negative 15 degrees Celsius, and what is it doing? The temperature's increasing to 0 degrees Celsius. So we have a change in temperature, which means we're going to be using Q equals Cm delta T to figure out how much heat it takes to make that temperature change. So we need the specific heat of ice. And if you go back to your chart of specific heat, you'll notice that ice has a different specific heat than liquid water. So we want to make sure we're using the solid water specific heat, which is 2.03 joules per gram degree Celsius. Okay, so that's the specific heat, and then the mass, 3.5 grams, and the change in temperature. Well, we're not going all the way to 35. We have to stop at that corner, so we're going from negative 15 to 0. Final minus initial means our temperature change is 15 degrees Celsius. So if you'll notice, the grams cancel, the Celsius cancels, so our units will be in joules. And when we do that multiplication, and we round to 2 sig figs, we get 220 joules. So that's how much heat it takes just to raise the temperature of the ice to the melting point. And then for section B, we're going to take all of that ice and we're going to turn it into water. So you're going to need to flip back in your notes, find the heat of fusion for water, and we're going to use that as our conversion factor. Now here, we need to convert our grams to moles. So we're going to start with our 3.5 grams over 1. Need the molar mass of water, which is from the periodic table, 18.015 grams. Then we can use the heat of fusion to get our kilojoules. And the heat of fusion for water is 6.01 kilojoules per mole. So our moles cancel. So when we do the calculation, we keep our 2 sig figs. We're going to have 1,200 kilojoules. Okay, so that's how much it takes to melt all of that ice and turn it into water. Now that it's all water, we can raise the temperature of the water. So we're going to look at our final little section of our graph. Because we're raising the temperature, we're going to go back to Cm delta T. Now this time, if you look at your specific heat chart, we do want the specific heat of liquid water, which is 4.184 joules per gram degree Celsius. Still the same mass. Now, our temperature, we've already gotten the temperature up to 0 degrees Celsius. Now we want to raise it from 0 up to 35. So this time our temperature change is 35 degrees Celsius. Again, the grams and the Celsius cancel, so we'll get joules when we multiply. 2 sig figs, 510 joules. Okay, now we're not quite done yet. We want to know how much heat is needed. Well, that means we have to add them all together. But if you take a look, this answer is in joules, this one's in kilojoules, this one is in joules. They all have to be in the same units. Oh, hang on, go back. I take that back. That should be 1.2 kilojoules, which is equal to 1,200 joules. There we go. That didn't look right. So now we have all three of our units are the same. We can add them all together. 220 plus 1,200 plus 510 gives us 1,930 joules of heat required to convert 3.5 grams of ice at negative 15 degrees Celsius to water at 35 degrees Celsius. We could keep going. We could raise the temperature of the water to 100. We could vaporize it. We could raise the temperature of the steam. So there could be up to 5 different calculations when you're doing a heating curve problem just like this.